converting decimal numbers to binary equivalents. So we're going to look at two different methods today in order to convert a decimal number to a binary equivalent. So our first method is to write out the place values. So we remember that it starts out with our 1 spot, and then as we move to the left, it increases by a whole double. So it doubles what the first thing is on the right. So 1 to 2s, 2s to 4s, 4s to 8s, 8s to 16s. Then we have 32, and then we have 64. And so what we're doing is we're looking to see 14 written as a binary equivalent. And so what we do first is we look at 14 and we see what the closest number it is in this. So 14 is close to 16, but it's not a full 16. So the next one would be an 8. So 14 has a total of a whole 8 in there. So we would represent this as a 1 in the 8th spot. And then what we do is we go 14 minus 8. And that will give us to 6. So then the next thing will be to look at 6 and to see if it has a whole, as we move to the right, if it has a whole 4 in there, which it does. Because we can go 6 minus 4, which is equal to 2. Then we see we have a 2. And we see we're at our 2 spot. And so we can take a whole 2 from this. So 2 minus 2 is then 0. Then we look at our 1 spot. We see we don't have anything left for our 1. So this is just a 0. As we can see, the number for our binary equivalent is 1110. Now let's look at another example. Example 2. Convert 75 to a binary equivalent. So what we need to do is write out our numbers. So this is our 1 spot, this is our 2s, this is our 4s, this is our 8s, this is 16s, this is 32s, and this is 64s. And then 2 to the 7th would be 128s. So when we look at 75, we see that it's between 128 and 64. So we're going to say it has a full 64 in there. So we're going to put a 1 below the 64. Then we go 75 minus 64, which is equal to 9. Notice that we have a really small number now. So that means that we're not going to be able to have a whole 32 in there or 16. So we'll just put them as zeros because we can't go ahead and subtract a whole 32 from a 9 or 16 from a 9. But then we come to 8 and we notice that this is 9 and this is 8. So we have a whole 8 in there because we can go 9 minus 8, which is equal to 1. Now we move to the right. We see we have a 1, so we don't have a full 4 in there because we can't go 1 minus 4. And we can't even do 1 minus 2, so this is 0, 2. Then we notice we have a whole 1. So if we went 1 minus 1, that would be 0. So we do have a 1. And so our binary equivalent is 1001001. We can write it like this. So that's our binary equivalent. Now let's look at a second method to find binary equivalents. Example 3. So our second method will include where we take our number and divide it by 2. and you're going to repeat this process. So let's look at example 3 to see how we do this. So we're going to convert 8 to a binary equivalent. So what we do is we take the number 8 and we're going to go ahead and divide it by 2. This gets us to a whole number 4. So anytime we have a whole number where there's no remainder, we're going to place a 0 for that. And then if there is a remainder of 1, we're going to place a 1 there. Now let's go back to this. So we have a 4. What we do is that's a whole number. So there's no remainder. So what we do is we start on the far right, and we're going to go ahead and place a 0 there. Next we take 4 and we're going to divide it by 2. 4 divided by 2 is 2, which is a whole number. So once again we get another 0 because we don't have a remainder. Next we take 2 and we're going to go ahead and divide it by 2. This is a whole 1. So this is a whole number, there's no remainder. So this will also be a 0. Then we take 1 and we're going to go ahead and divide by 2. Now 1 divided by 2 is not a whole number that it comes out to, that there's a remainder. So it's 0 and a half, or 0 with a remainder of 1. So what we can do is, because it's closest to, the whole number is going to be 0, but we have a remainder, that means we're going to place a 1 right there, because that's the next spot. And because we're at 0, we're done. So this is our binary equivalent. Let's do another example. Example 4. Convert 60 to a binary equivalent. So what we do is we're going to take 60 and we're going to go ahead and divide it by 2. Then we get 30. This is a whole number. So we go over and then we're going to place this in our first spot on the far right. And we're going to place a 0 there because there is no remainder. Then we take 30 and we're going to go ahead and divide it by 2. And we get 15. 15 is a whole number. So we're going to go ahead and place a 0 there. Then we take 15 and we're going to go ahead and divide it by 2. Now this is not a whole number. So this is when we're going to have a remainder. So the whole number, when you go 15 divided by 2, it's 7.5. So we're going to put a 7 there. And we're going to go over and place a 1 below because we have a remainder. Then we take 7. Then we're going to go ahead and divide it by 2. Then this is 3.5. So we have a remainder. We're going to put 3 because that's the number. And then we're going to go ahead and place a 1 here. Next we take 3 and we're going to go ahead and divide it by 2. This is close to 1.5. Or it is 1.5. So we're going to go ahead and place a 1 there. And so that means that we have a remainder. So we're going to go ahead and place a 1 there. Then we go 1 divided by 1. Then we go 1 divided by 2. And that is 0 as our whole number, and then a half. So we have a remainder as 1. So this will be 0 because it's the whole number. And then we need to go ahead and place that with a 1 because it has a remainder here. So our binary equivalent to 60 is 1 1 1 1 0 0.